Physics 2212, Lab 3, Circuits. Introduction. Purpose. The purpose of this lab is to use the principles of energy conservation and current conservation to predict and examine the behavior of ohmic resistors and capacitors. For this lab, we will be using a circuit construction kit, CCK. Physics principles that we'll be using in this lab include the node rule and the loop rule, both involving conservation of charge and energy. The first one, the node rule, I will use in the diagram on the left or on the right to explain. With this black node here, we see that the current going into it has to equal the current going out from these two branches. This comes from the node rule, and it goes for all points on this circuit. For the loop rule, for any loop that can be made in a circuit, the potential difference around that loop has to equal 0 if the start and finish are the same point. For results preview of this lab, the RC value of the final circuit is found to be approximately 6 seconds. Following part of the lab, we were asked to predict the current in the following circuit and then build it in the CCK and compare the results. As we can see here, this is the original circuit. It involves two 1.5 volt batteries and then two resistors, one with 47 ohms and one with 100 ohms. When we do this, by solving using the loop rule and the node rule, we're able to find that the I is equal to 0.0204 amps all across the circuit. When we build this in the CCK, we find that we get the same exact results. Parts 3 and 4. 3. Reversing the ammeter does not change the values of the current. This is because the current measures the charge's speed at which they move, so the way it is oriented does not matter. 4. When we instead close the circuit with a voltmeter rather than an ammeter, we find that there is no current showing in the ammeter and a voltage showing in the voltmeter that is not 0. This happens because the circuit is not closed, so no current can flow through, but there can still be a potential difference in the circuit. Here's a picture for part 4, where it shows a non-zero voltage in the voltmeter and a current of 0 showing up in the ammeter. 5 through 7, we are now tasked with replacing the voltmeter and ammeter from before back with wires, making a regular circuit. We then find the potential difference across the points from A to B, B to C, C to D, and so on. When we do this, we find AB to equal 3 volts, BC 0 volts, CD negative 0.96 volts, DE 0 volts, EF negative 2.04 volts, FG 0 volts, and HG 0 volts. Through this, we see that these voltages add up to 0, which is explained by our loop rule, as we see that if we go from point A all the way across to point H, we have completed a loop around the circuit. We put our results from part 7 into a graph, and as we see here, we can see that our results show the voltage drops to 0 as it goes throughout the loop. We connect our ammeter. We see the current drop in the ammeter, because according to the node rule, the current going in has to equal current out. So because there is a split in the wire, current is also split. Following this, we calculate the resistance of the two resistors, the wire and the ammeter. We find the 47 ohm resistor has a 47 ohms of resistance as predicted, as the 100 ohm resistor also has a predicted value of 100 ohms. The wire and the ammeter have a non-zero value of resistance, but it is so small it is negligible in this scenario. We found that it takes 6.6 seconds to charge the capacitor with a 10 ohm bulb and 7 seconds to deplete it. For the 20 ohm bulb, it takes 13 seconds to charge the capacitor and 13.8 to deplete it. We also see that as the capacitor is charging and discharging, the current continues to drop until it reaches 0. And the RC value, or the time constant of the capacitor, we start by setting up a circuit with a 9-volt battery, the bulb, and a capacitor in it. First, we charge up the capacitor until it is full, and we take out the battery, and then let the capacitor discharge. We check the voltage in intervals of 1 second for 20 seconds, then we record it. We then plot it by plotting the natural log of the potential difference over the initial potential difference versus time, and we find a slope of this line. When we take the slope of this line and do 1 divided by the negative slope, we find the RC value, which is 6 seconds for this capacitor. This question asks the difference between an actual ammeter and the one we use in our model. Well, a real ammeter would provide some resistance, whereas the one in the model provided almost none, which would change the outcome of this lab. Our second question asks the same, but with a battery, and how things would change. Without a resistor in this online circuit, the capacitor would charge instantly with this battery. However, in real life, batteries do have some internal resistance.